So last time we had talked about finding the wavelength of an electron. So we're going to go continue on that. I've got some videos. I've got some spreadsheet problem working out to look at. And in particular, we want to look a little bit on Fourier analysis, which you should have had in your mathematics classes, and which for the electrical engineers in here, you're going to get a whole lot more of. Because Fourier and Laplace play a main portion in electrical engineering. Fourier plays an important part in what's known as system and signals. Laplace plays an important part in switching circuits. Fourier is basically frequency analysis, and one of them really works frequency analysis to do filtering and such. And in quantum mechanics, Fourier plays an important role. In general, it's a way of solving differential equations. But what it does is turns the problem either into something that we understand better and can think of, such as frequencies, rather than when a wave comes in, what are the frequencies that are composed of the wave? Or it makes, hopefully, the math problem simpler. So with that, I'll talk a little bit about Fourier and a little bit about the other stuff in the chapter before we see part of the video that I want to look at about Fourier. So, an overview of Fourier analysis. Fourier analysis of a function, take the Fourier transform, says that if you have a function that depends on x, you can multiply it by e to the ikx, a plane wave. And you can integrate that from minus infinity to infinity with respect to x. In other words, integrate it over all space. And here's the thing, if you integrate it over x, then there won't be any x left after you've done the integral. So what you get is a function that now depends on k, the wave number. Now, why would anybody want to do something strange like this? Well, the reason you might want to do something strange like this is that if you have a differential equation, say the second derivative with respect to x, and you do this weird thing to the whole equation, you can convert an equation that has calculus into an equation with algebra. So in other words, you can take a second derivative, second order differential equation, and turn it into a second order polynomial, and you have the quadratic formula to work. And you know how to work that problem. Now here's the thing. After you work the problem in k-space, it's like you've gone to a foreign land. You've used this to cross the Mexican border. You've now bought all your stuff in Mexico. But you have to get back to the original problem, back into X land. That is, you have to cross the border again. And the question is it harder to cross the border than it was to solve the problem? If the answer is yes, then this process doesn't make any sense. And if the answer is no, then it's a great way to solve hard math problems. So one way, you take this transform, you cross the border, you get a new equation, you solve that equation, and then you cross the border again by doing what's called the inverse transform. So here you see an e to the minus ikx. You integrate over k, all the different wave numbers, and you end up back with the function f of x. So the idea is kind of shown on the other page. You've got a hard problem in x. You could just work the problem, solve the differential equation, do whatever trick you learned in DE class. But it's hard. So you take the transform to get to a function of k. This equation in k turns out to be easier. You solve it. But you weren't asked to solve for k. You were asked to solve a problem such as the position of a particle. So then what you have to do after you've solved the problem is you have to take the inverse transform to get back. There are all sorts of different transforms depending on the type of problems. Some of them go e to the ikx, that's Fourier. Some of them go e to the minus st, that's Laplace. There's z transform, Hankel transforms. Take any field of engineering or science, and there will be transforms that have been found useful for their type of problems. The ones we care about are the ones that deal with waves. The ones that deal with waves are foyer. Now, everybody knew this was possible. So people had, for instance, had problems involving balls thrown through the air. And they would solve that differential equation by this trick. And when they did that, they would find that there was a wave number for the baseball because you put it in K-space, but that didn't matter because baseballs don't have wave numbers. And then they would solve this problem and take the inverse and get whatever the solution they needed, such as the velocity of the ball, the position of the ball, or whatever. Nobody had a problem. They also know about another thing. If you have two variables, like K and X, they're related by an integral transform. Let me move this up. This transform pair. Then there is an uncertainty relation between the two. The uncertainty in the K and the uncertainty in the X are always greater or equal to 1/2. What does that mean? That means that what you're doing here is summing up a bunch of waves to make a function. If the function is very narrow, it will take a lot of waves, because you'll need some waves to constructively interfere and some waves to destructively interfere. So if you wanted to know the location of a baseball with great precision, you had great uncertainty in its wave number. That's just the way the Fourier transform works. People said, so what? Baseballs have no wave number. Baseballs have momentum, yes. They have position, yes. Wave number, no. That's just an artifact of math. What's happened now, though, with de Broglie, he said, hey, hold on. P is H bar K. So if there is uncertainty in K, there's now uncertainty in momentum. And momentum is something a baseball surely has. So it's not that this relation was new. It's that relation, the wavelength statement of de Broglie. And the problem is, experimentally, Davison and Germer and G.P. Thompson have proved this. So now we have a weird relationship called Heisenberg uncertainty principle, which says you cannot both know the location of a baseball with absolute certainty and simultaneously know its velocity. Think about that. That's very bizarre. You cannot know both where something is and in what direction and how fast it is going at the same time. Go back and look at classical physics for a minute. We started this whole thing by saying, oh, we put a coordinate system. And there'd be a ball here. And there'd be a position vector, R. And then we could take its derivative and we could find B. And if we knew B over some time, we could figure out where the ball is going to be some later time. And if we wanted to figure out what the ball was going to do after that, we needed to know a new B. We had a relation by that. F was equal to MA. M dV dt. So if we solved that, integrated it with respect to dt, we got the change in the velocity. So with that relation, Newton's second law, I can tell you what the new velocity was. Maybe it's like this. And then I could step another unit at a time and go over here. And I have a new R. And I have a new B. And so on and so forth. It's deterministic. Tell me where it's at and tell me which way it's going, and give me a relationship, and I can tell you what's going to happen in the future. It runs like a clock. Quantum mechanics says that that's dead. It cannot be true. You cannot know this and that with ultimate precision. It has nothing to do with how good of an instrument you can build. It is a fundamental limitation to your knowledge. Now, the interpretation of that is still highly debated. There are physicists who believe that there is no deep underlying reality, that the very act of measurement creates reality. There are others who believe that there is deep reality, but that there is a limit to what you can know. What we do know, I don't know about philosophy, but we doggone sure know how to calculate and apply this quantum mechanics to solve problems, to build devices, to make modern electronics, to make lasers. So in that sense, it works. But the philosophical about what is reality, what does it mean to have position? What does it mean to have velocity? That is still highly debated. Right? What it is definitely certain is you can't just tell me the starting point and I can know everything from then on with absolute precision. It is not possible. I can know with probability. The idea of deterministics is gone. Now, Einstein did not like this. He hated it, in fact. He argued along against it. He gave a series of experiments. His last one was called the aspect experiment. And that experiment couldn't be done at the time. It was done in the 1980s, and Einstein's determinism was shown to be incorrect. And Bohr and quantum mechanics was shown to be true. All right. I left a lot more in your reading. I didn't plan to go through that. I don't think it's necessary for me. I want to at least do a little bit of the math like the book does. So one problem is that someone could give you is take the Fourier transform of a particular shape. The book chooses a function that looks something like this. I've slightly modified it. That could be a probability distribution function. It could simply represent the location of a particle somewhere in this box, or it could represent a digital pulse, if you're one of the electrical engineers here. So it goes like this, it goes up like that, goes up like this, goes down like that, and goes over. And what I would like to know is if I was to try to represent that as a sum of sines and cosines, what would I have to do? How many waves would I have to have? How big would each one of the waves have to be? How can I add some waves to make it where this looks like 1, but there's no probability that the particle is out here? How could I do something like that? That's my goal. Now, to show you kind of how I would do that in a bigger sense without doing the advanced math, I have a problem that's in a spreadsheet here. And instead of just having one square, I have a bunch of squares here. Like that. And I want to add some sines and cosines to try to reproduce that function. So the first question is, what do you know about this function? Is it an even function or an odd function?
Odd.
I heard an odd and I heard an even. That's good. That was the two possibilities. Want to give me one of the others? What is it? Well, that's really bad. If you guys don't know what an even or odd function, somebody should have shot your math teachers.
It's odd.
It's what? How do you know it's odd?
Because it's not centered at the origin.
It's not symmetrical.
It's not symmetric around 0.
It's not symmetric around 0. That by itself does not make it an even or odd.
It looks like sine and sine not a function.
Go back, pick up use math for freshmen, and go back and reread that section on even and odd functions. Function is even when you put the negative argument this is the same as that. The function is odd when you flip around the y-axis, you get the negative of the function. Not everything is even or odd. There are lots of functions that are neither even nor odd, okay? But they can always be broken down into a combination of even and odd functions. Why is that useful when you do Fourier? It's useful when looking at Fourier series because the cosines are even, the sines are odd. So if you know the function is an even function, it can only have cosine terms. If you know the function is an odd function, it can only have sine terms. And if it's neither, you need both. So it helps you quickly identify whether or not you have to do a whole lot of math work or a lot less math work. So back to my desktop problem here. This is an odd function because if you take a value of x, like say right here, you get 1. But if you went to the negative x side there, you get a minus 1. It's the negative of the function when you flip it about this axis. That means there are no cosine terms, only sine terms. Now, I can choose different values for those sine terms. I'm going to choose one. I'm going to choose frequency of n equal 1 and a function of 1. And that's what I get in black. And it's a sine function, and it fits kind of pretty good. But it has some errors. You can see that it doesn't fit very well over here. It undershoots. And it doesn't reach down here. Now, this guy very nicely, in his quantum thing, has developed a little graph here that shows the errors. So there's error, a lot of error here, no error there, a lot of error here. And even gives you a numerical value for how much error there is. Now you can change, and I'll send you guys this little spreadsheet, you can change the n's to something else, like make it 2. Now what's wrong with that? Is that better fitting the red graph, or does it fit it worse? Fits it worse. Why? It's out of phase. What's it wiggling? Is it wiggling at the same rate? Twice as fast. So that's not a good choice. So let's go back. Now it wiggles too fast. That's why it's really undershooting here. You can see our numbers got a lot worse. So let's put that back at 1. What if I add another way? Well, you can add different ways of different values. So now it's overshooting some places up here. It's undershooting some places there. Doesn't really look very good. If I change that to 3, now I get a much better fit because I don't have anything going out here. I still am undershooting a little bit there. I'm overshooting a little bit here, undershooting here. I could play around and just keep adding more and more waves, and I can get this to look closer and closer to the value without any math. What the Fourier series and transform does is provide a way to find these values of A and N systematically rather than me play, let's make a guess. But I can make a guess, and I can come pretty close. Hey, I'll try 5 here. And maybe 0.2. Look at my error number, got a little better. A little better still. Look, that's worse. The more waves with the more different wavelengths and hence more momentums, the better it fits a confined wave with a limited delta x. That's all Fourier analysis is. Now, if you have a periodic wave, that is a wave like this, then you only need discrete wavelengths to make it fit, and it's called a Fourier series. If you have something that's aperiodic, that is, it doesn't repeat, you will need a continuous set of waves, an infinite number, and you need what's called the Fourier transform. So that was a periodic one. The one in the book that he's doing for a problem that I modified is an aperiodic one. So that's the one I'm going to do on the document canvas. But I'm going to try to just find those waves, what those values of A and N are. So, I don't have a periodic wave, I have a discrete wave. I ask you, what is the Fourier transform? Of this function. Okay, well, by definition, the Fourier transform is defined to be 1 over the square root of 2 pi, the integral from minus infinity to infinity, whatever the function f of x is, times e to the ikx dx. You'll notice I'm not doing sines and cosines. This is sometimes called the complex form of it. These e to the ikx's are related to sines and cosines. They're the cosine of kx plus I sine of kx. There are also plane waves. If you have a minus omega t out here, you'd have a plane wave. So what I want to do is I want to find out how many of these for different values are in those. What I'm going to do is I'm just going to put in the value of f of x here. So it's 0 until it gets to minus x over 2. Then it's 1. And then it's 0 after it goes past delta x over 2. Still have my square root of 2 pi, but now it starts at delta x over 2. Goes till it gets to delta x over 2. In that region, the value of f of x is 1. So I get 1 times e to the ikx. Which is that. Now, why did the book like this? Of course, he did it over k space, and I'm doing it over x space. He liked it because this integral is easy to do. This is something the students should know how to integrate, an exponential function. It's also kind of a useful thing because this is a digital pulse. So for electrical engineers, we got digital logic here. This is computers, right? And so in computers, this would be time up here instead of space. And what we would be transforming it into is frequency. And when you mess with frequency, you get what's called filtering. So you go low pass, high pass, and band pass filters. In the quantum problem, this could be thought of as a confined particle in a box that we had a while back, where he's stuck equally probable to be in this. And what we're asking you then is, what are the k values, which when multiplied by h bar says, what are the momentum values for particles in this box? We'll come back and do more of that in the upcoming chapters. Finishing the problem, we got 1 over the square root of 2 pi. And the integral of an exponential is the exponential, so that's nice. over ik. We're evaluating it for minus delta x over 2 to delta x over 2. F of k is 1 over the square root of 2 pi. Put that in to there, and I get e to the I k delta x over 2. And then minus, I put that into there, e to the minus ik delta x over 2 over ik. And in the book at this point, he starts skipping some steps. When I look at that, I look at something that looks like e to the ix minus e to the minus ix. Now there's a math function that looks like something like e to the ix minus e to the minus x over 2I. What's that called?
Euler?
Huh?
Euler?
No. Well, Euler representation, but what's the function? E to the ikx minus e to the minus ikx over 2I called? Sine function. It's a sine function, you're right. So, if I multiply this by 2, put a 2 up here, then this quantity divided by 2I is the sine. So this thing's going to wiggle. Since I told you this is related to momentums, that says that there are varying different values of momentum. For every different value of k, and k goes from minus infinity all the way up to plus infinity. The minus ones would indicate particles going, for instance, in that direction, and positive ones would indicate particles going that direction. And there'd be lots of different ones. Now, for free particles, and their energies are p squared over 2m, they also have lots of different energies. Something else that's interesting. What's the value of this when k is 0?
2 over the square root of 2 pi?
Huh?
2 over the square root of 2 pi?
No, it's not 0 over the square root of 2 pi because it's 0.
I said 2 over the square root.
2 over the square root of 2 pi. Yeah, I would agree with you. Because what is this equal to?
1.
So this thing can be equal to 1. So what we need to, actually it's not quite 1. We need to actually slightly modify it. This thing does not go to infinity when this goes to 0, and it doesn't go to 0 when this goes to 0. What people like to do is, and what the book did by skipping a bunch of terms, is they like to put this argument in the bottom here. So that's k delta x over 2. They want to put a delta x over 2 down here. Well, let's see, I got the 2 there, but I don't have the delta x. So what he decides to do at this point is he says, hey, I'm going to multiply by delta x over delta x, and he leaves that out. In fact, he leaves out all of these steps. Then I have delta x over the square root of 2 pi sine k delta x over 2. And on the bottom I have k delta x over 2. Now why did he do that? This is one of these functions that if you take mathematics or elsewhere, you take any of the other courses, differential equations, you should have seen it, that are well known. They have names. It's called the sinc function. S-I-N-C. People call it cinch. And people who work a lot with Fourier transforms, such as electrical engineers and physicists know the shape of that right off their head. It looks like this. It wiggles, but it decreases in amplitude. You see that in optics. When you shoot things light through a square aperture, this type of drop-off in intensity type stuff. And it's for the same thing. They call Fourier optics, in fact. Fourier was involved in that sort of stuff. So you've got this, and then you have delta x over the square root of 2 pi. So that's really what you get, not the one for the 1 here. So it's very bright here. So what's the main momentum in k-space? It'd be 0. But there will also be negative momentums of certain amounts. You think of them as little arrows adding up. And there'd be some bigger momentums in the negative, and some bigger momentums in the positive. And they would go on, but it would have some uncertainty, if you would, much like with the bell curve. And it's that uncertainty and this uncertainty in x that multiplied together has got to be greater or equal to 1/2 for any function you put into this thing. People knew that, didn't bother them. It only is a bother because now this f of k isn't some arbitrary thing. Who cares about f of k? Nobody. But who cares if I multiply that by h bar? Everybody, because this is now a function of p, the momentum. And that's just multiplying everything by a constant. So that shape of that graph and the shape of this graph are the same. So this wave number, which had no physical meaning, just a math oddity, now has physical reality because of de Broglie's famous equation. So we get into problems with something that seems so simple. A photon is also, it's a wave, electromagnetic wave, it's also a photon, a particle. Then let's turn it around. The particle can also be a wave. That doesn't seem that complicated. And then we found experimentally that the equation worked. But now it has implications in problems that we were solving for a long time. Profound implications that limit what you can know. Make sure you can take the Fourier transform of a simple thing, and for you electrical engineers, as well as physicists, you should put this to knowledge. The Fourier transform of a pulse, a square wave, is a cinch. By the way, the inverse is true. The Fourier transform of that is this. And I don't care whether it's in omega and t, or k and x, or whatever two variables are connected. This shows up all the time. Physicists like to build chopped pulses of laser light or else particles that are chopped. They turn the beam on, they turn the beam off. They chop it. And they're going to get this implication. Electronics people like to chop things on and off. Let's say that this is time. They want to make a faster circuit. So they shrink this. Fine. But if you shrink this in time, you expand that in frequency. So you have to have a high bandpass system. That's why people talk about, hey, you got to have high bandpass communication. That's because you want to send a lot of data in short pulses. This is a fundamental connection between two types of spaces that you can never get around. It's a limit to the universe we live in. You can't build a better detector. You can't build anything. Quantum mechanics says it's there and it will always be there. Energy and time, position and momentum, they're connected by this Fourier transform. Now, Heisenberg and his guys would go on and show lots of things have this complementary type aspect that don't fit the Fourier transform. And we'll deal with that in quantum class. But all we require you to know is the two for this class. And that is the position and momentum, which I derived from the Fourier. You should know this. And you should know this one. Energy and time. So if you want to know exactly, with great precision, the energy difference that a photon gives off, then that photon's time or probability it ever makes that jump, the time is going to go huge. And if it was absolutely zero, it would never make that jump. It would take infinitely long. So these energy levels we drew last time can't be levels like that. They have to have a width to them. And we can in fact measure that. And by measuring these energy widths, we can learn about the transition times in nuclear physics. And by learning about transition times, we can turn it around the other way. And we can learn about uncertainties in the energy levels that we can't see. So people use this in solid-state physics and nuclear physics a lot. So get used to thinking about it. All right. Good stuff. Tricky stuff. Quote Niels Bohr. He said the following thing about this whole stuff. He said, anybody who's ever seen this and isn't confused by it didn't understand it. All right? Takes some getting used to. If you think it's easy and you just, oh, that's just no trouble, you don't know what the heck you're doing. You haven't spent enough time thinking about it. There's a lot more information back in the Feynman lecture series. If you look in book 3, there's a lot more in Iceberg and Resnick. There's a lot of stuff online. People spend a lot of time thinking about this. There's a thing called Challenges of Quantum Mechanics that I put down in the SPS ring. You can go through that and look what modern people are still fighting over questions of determinism, causality, and so forth in interpreting what quantum mechanics means. One of the speakers at the conference, Dr. Scully, will be discussing how you get to various formulations of quantum mechanics and their impact. All right. Moving on.
When is that conference?
It's April 4th through the 6th. 4th is the social that night, and with the SPS, we have 2 groups coming in from Arkansas. There's at least 2 groups now coming in from Oklahoma, as well as the students from Texas. So we'll have the thing. I don't know how they're going to work out the land playing all night long, but the food and everything will start at 7. And then Friday is the main set of talks, Friday and Saturday. We have a star party Friday night after the banquet.
But this explanation of the photoelectric effect not only confirmed Planck's theory, it showed directly that bundles of energy already exist in the electromagnetic field. In other words, light comes in particles which are now called photons. But wait a minute. A century earlier, Thomas Young had proved light travels in waves. Was it now going to turn out that light is really made of particles after all? Perhaps this whole business of particles and waves was in need of an entirely fresh perspective. Louis de Broglie got a history degree en route to a career in French government, a fresh approach to physics if there ever was one. Maybe that's why, in the 1920s, he was the one to ask a crucial question. If light waves can be particles, is it possible that particles, such as electrons, can also be waves? To begin with, particles have energy and momentum, while waves have frequency and wavelength. Obviously, these entities have different kinds of properties. But de Broglie suspected there was some sort of connection. And Planck's theory had given a clue to what it might be. Max Planck had associated the energy of a light particle with the frequency of its wave. Going a step further, de Broglie combined this with the particle's energy according to Einstein's relativity theory. E equals mc squared. This bold mixture of wave and particle properties suggested the next step. Could particles traveling at less than the speed of light have their momentum related to their wavelength? De Broglie believed so. He thought that just as a particle's energy is related to a frequency, a particle's momentum is related to a wavelength. It was a radical idea. Not only can light waves behave like particles, but particles can behave like waves. But within a year, experiments had verified that beams of electrons could be diffracted much like beams of light. And even beyond that, de Broglie's ideas seemed to explain a most mysterious aspect of Niels Bohr's model of the atom. Bohr's theory was built on the notion that electrons can only exist in certain sized orbits, only in those orbits and nowhere in between. But if electrons are viewed as waves circling the nucleus, they have to exist in orbits that increase a whole wavelength at a time. That way, each orbit consists of electron waves that interfere constructively and reinforce themselves on every orbit. When combined with de Broglie's formulas, this idea exactly reproduced the orbits of Bohr's model of the atom, because the angular momentum of each orbit would be an integer times h bar. On balance, Louis de Broglie's idea had been brilliant. It had given an insightful and elegant explanation of Niels Bohr's model of the atom. It had been supported by solid experimental evidence. And, not surprisingly, it drove other physicists ever deeper into the nature of matter. In Austria, Erwin Schrödinger pondered the implications of the Frenchman's work and produced a theory of his own that took off from de Broglie's ideas. A wave has an amplitude and a wavelength, but no beginning or end, and nothing like the definite position of a particle. That remains true if a wave of the same wavelength is added, either in phase or out. But if waves of different wavelengths are added, the resulting shape is altered. And if those wavelengths are close together, and especially if more waves of nearby wavelength are added, the result can be a kind of wave concentrated in a limited region of space. So with a range of wavelengths, and therefore a range of momenta, a wave-like object can be constructed in a fairly definite place. But because it has a range of momenta, it spreads out as it moves along. It isn't really a particle, and it isn't really a wave. What in the world is it? It is the clearest possible description of the nature of photons and electrons, of the matter which makes up the universe and everything in it. And as an idea in 1926, it was the heart and soul of Erwin Schrödinger's wave mechanics. Light passing through two slits causes an obvious wave interference, which clearly reveals itself as a pattern of light and dark stripes. there is no question about light being a wave. Only waves behave this way. So the question is, how can light be particles and still interfere like waves? If light is made of photon particles, individual little things which can't arrive as a spread out pattern, then each particle has to hit the screen individually. A single spot of light here, for example, another photon there. It's impossible to predict precisely where any spot will appear, but it is possible to see that more photons land in some places than others. In fact, there's a higher probability that more photons will land in certain regions. And eventually, because of those probabilities, the result will be a definite wave-like diffraction pattern of particles. This was the explanation proposed by Max Born. Photons might be particles, he said, but the patterns they make are ruled by probabilities that interfere as waves. And one of Born's colleagues, Werner Heisenberg, took that idea one step further. Because particles are associated with probabilities that interfere like waves, he said, it's impossible to know both the exact momentum and the exact position of any particle at the same time. The idea may be a little hard to grasp, but that was just the point. Particles, being waves as well, are a little hard to grasp. The nature of a regular wave with a definite wavelength is to spread out in space. If this wave represents a particle, then its wavelength translates into a definite momentum. However, nothing here accounts for the particle's location. The particle's place can be made more definite by adding wave after wave of different lengths. But each new wavelength means a new momentum. In other words, the more one knows about where a particle is, the less one can tell about where and how fast it's going. As the position of the wave becomes more definite, the momentum of the particle becomes less so. That relationship, delta x times delta p is approximately equal to h bar, is called the Heisenberg uncertainty principle. Werner Heisenberg, searching for deeper scientific truth, had raised uncertainty to the level of a fundamental principle of nature. But the irony of this story lies elsewhere. Drawn to something universal in the nature of all glowing bodies, Max Planck discovered that light is radiated in little bundles of energy. When Albert Einstein solved the photoelectric problem, he confirmed that Planck's energy packets exist as particles in the electromagnetic field. Combining the insights of both Planck and Einstein, Louis de Broglie suggested that not only could waves behave like particles, but that particles could behave like waves. Erwin Schrödinger understood that if enough waves of different lengths are added together, the result is a wave that's concentrated in one or another place like a particle. Then, Max Born saw that while it's obviously impossible for one particle to create a visible wave pattern, a cluster of particles, whose behavior is determined by probabilities, can fall into a pattern that looks very much like wave interference. And in that very fact, Werner Heisenberg saw the trade-off between the particle quality and the wave quality of light. When the uncertainties of position and momentum are combined, the product is approximately equal to Planck's constant. And that, beginning with Max Planck's constant and coming full circle, is the irony. Planck's quest for truth became a journey that led to the heart of quantum physics. Yet to the end, he himself never accepted the profound implications of his own work. And for that matter, neither did Albert Einstein, who said, "It seems hard to look in God's cards, but I cannot for a moment believe that he plays dice as the current quantum theory alleges he does."
Okay, last thing for the day is that you got homework due tonight. I will give you new homework, but I will not make it till after spring break.
Oh,
If you want to start it early, you can, but you got exams to get ready. And so nothing is due next week so that you can concentrate on your exams. If you want to get ahead because you're going to go somewhere spring break and ski or what have you, you can do that as well. So I'll try to get that up by the weekend. All right, see you later.
Our test is going to be next week as well?
Yep, we'll select the time on Fridays. Pretty much till 8 o'clock at night, I'm here, so no problem.
So next Friday, or this Friday?
I think by Friday, I'll send you out an email, you guys can select the time, and we'll take it together as one group.
Okay.
I haven't yet finished making it out, and I'll take exactly how much time that everybody will be allowed to do that.
Okay.